basic, too acidic, or it's too much salt. Sometimes some will work in it, others will not. Because buffer 3, because these two work at 100%. And what was important of adding water was get the concentration just right. Buffer 3 from within the vial itself is actually highly concentrated, and if you were to add Bago and Echo into pure buffer 3, it wouldn't work so well. So we used the water to dilute it, and that's why I was so nitpicky about it being 20 microliters when we did the digestion, because concentration is extremely important for it to function, for the reaction to take its place. So we ran the reaction, 37 again overnight, and the following week we performed the gel electrophoresis to separate the DNA. Now, for this part, I first made you guys a gel which with 1% agarose, with 1 times TAE and ethidium bromide, and that was about 1.5 microliters per the 50 ml of gel that was made. At the very top of these gels, we had a whole series of columns where we had you guys inject your digestion plus loading dye. Now loading dye, just like the buffer, is also highly concentrated. That's why we had you add specifically 4 microliters to the 20, because this was 6 times and needed to be reduced to 1 times. So you ran it in here. Now because DNA is negatively charged, we would have to set the anode at the top where the wells were and the cathode at the bottom, so the DNA would travel in this direction, not out of the gel quickly like that, but towards here, using the loading dye as a marker of where the DNA is traveling. Now, what was unique about the gel is that it is sort of a lattice in such that the smaller molecules of DNA can move through faster, while the larger ones are impeded and move through much slower. So what you would see here is that the big DNA, which was your backbone, will get stuck, say, up here. Where it's this, so it's clear. And your smaller band would go down further down here. Now, besides the DNA that we had, your DNA, we also included a ladder. Now, what the ladder does, it serves as a marker, so you can determine the sizes of your DNA, and also, to a lesser step, which you're not doing here, but also look at the concentration of DNA sometimes. Now, all right, good enough. Now, what I want you guys to do for the lab reports, well, what would really be helpful first is create a chart. And this is very important. There's 3 columns. In the first column, you're going to take the base pairs of your ladder, which will be these guys here. Now, to make the standard curve, I suggest a minimum of 5 marks on the ladder, but the more marks, more dashes you use will give you slightly better and more accurate equation, but at least 5. That's what I'm hoping you guys do. Now, for the sizes, you have to go on Blackboard, and there is a map for the 1 kV ladder, because that was the ladder we used, and it'll tell you which mark was what, and you can actually look at the concentration, because was it 1,000 that was the heaviest?
The smallest piece is 500.
Smallest piece is 500?
And then it's 500, 1,000, 2,000, no, 1,000, 1,500, 2,000, 3,000, 4,000, 5,000.
Which one was the brightest?
3,000.
3,000. So what would probably be a good idea to do is look for the brightest mark on the gel and compare it to the brightest one on the pamphlet, and you could determine which one of these marks is which size, and that will be your first column. So we say we got 1,000, 1,500, and 100 here. Now, in the second column, what you're going to do is measure the distance from the well to the very front of each corresponding, so to the very front part, most bottom part of the mark. Don't go to the top, to the very bottom of it. And you're going to measure the distance in millimeters, so you print up the gel, and measure from the well for each one of these bands, and it'll give you a certain distance. Please do this one right, like 10 millimeters, this would be 5 millimeters, this would be 2 millimeters. So distance in millimeters. Now, in this third column, what you're going to do is take the log base 10 of the base pairs. So what you're going to do is take these values and take the log 10 of them, and you'll give you these values, which will be 3, 2, and 2. Now, these values in these last two columns is what you're going to make a plot out of. For the plot, I made that too big. What you're going to do is on your x-axis, you're going to put the distance in millimeters. And on the y-axis, you're going to take the log 10 base pairs, and you're going to get a graph that's going to be like this. So, line graph with a negative slope. Well, actually, this line is actually going to be your trend line. So actually, let me backtrack just a second so I make this a little clearer. You're going to plot each one of these points, and when you put in your trend line, you're going to get a line with a negative slope. Now, just like in the slide slide before, we want an r squared value as well as an equation, and the equation is going to be y equals something x plus or minus another whatever value. Now, with this equation that you've determined, just over here, you're going to measure the distances of your bands at the very front like you did with the ladder. And you'll plug these in for x and solve for y. Now that's going to give you the base 10 of your band sizes, so all you have to do is take the inverse log of them, and it'll give you the sizes of your bands in terms of base pairs. So don't forget to do that last step, because if you don't take the inverse log of those values, you didn't do all the work, you're not complete. Yes?
Can you repeat that one more time?
Yeah, sure, no problem. That is one of the most important parts. So once you, okay, so go back to the equation. So what you're going to do is take these bands, distance in millimeters, you're going to plug them into x into your equation, and you're going to solve for y for both of them. So you're going to get either one or two values depending on how many bands you get. Then what you're going to do is take the inverse log of those values, which is, I think it's essentially,
Excel will do it.
it's 10 to the, it's 10 to that value, that's what it is.
I can't remember how to do it. Excel's got a formula.
Yeah, they have a formula, but I'm pretty certain it's 10 raised to the power of whatever those values are. So 10 to the y, and that will give you your base pairs of your bands. Does that look clear?
So can somebody pull up your, well here, so somebody needs to pull up the 1 kb ladder from Blackboard on their computer, and we'll kind of show you what we mean by all this. So it's under course documents, scroll down to gel electrophoresis, the 1 kb ladder NEB. So we've got it over here, so if everybody can kind of come over here so you can see. Your handwriting?
Yeah.
Yes, it is.
She knows.
I thought I had bad handwriting. Oh. Scroll down, please. Thanks. I've got a little knob button. Okay. So everybody can kind of come around here so you can see. What this document is, it's the 1 kb ladder information. And what you'll see on here is you'll see that they've got lots of different ladder information on here. We've got the 1 kb ladder, which is all the way over to the left. And what you'll see is there's a 0.5, a 1, a 1.5, a 2, a 3, 4, 5, 6, 8, and 10. Those are in kilobases. You have to convert those numbers into base pairs. So 0.5 kilobases is 500 base pairs.